Okay, let's get started. So today's your exam. If you have Friday recitation, if your recitation is today, make sure you're there 15 minutes early. Give yourself plenty of time for the exam. About an hour and a half. Okay, so about an hour and a half. It covers everything through Wednesday's lecture. But you know what? Most of today's stuff, we kind of introduced a new idea, but most of today's stuff is all good stuff. It's all valid for the exam. The new idea today builds on lots of stuff we've done already. So think about, you're still preparing in today's lecture. Okay? There will be, and then Monday, same deal. You go to recitation 15 minutes early. Then there'll be like a short web work and a short written assignment for Wednesday. Okay? And I'll put those up later on this afternoon. So, any questions about today's exam or anything like that? Okay, so let's just take a couple minutes to look at this sheet. It's pretty important. Hopefully you got a chance to look at this. So it says, let F be the number of people expected at a local concert if the temperature is X degrees Fahrenheit, and let G be the total revenue in hundreds of dollars at the concert if the attendance is X number of people. Determine if the expression is a valid process. So all these expressions are created from the functions F and G and their inverses, and what we're after is, does it make sense? Is it a valid expression or not? And then if it is, describe the meaning of the output or the meaning of X as it applies. So for those that are valid, we want to kind of unfold it and describe what's really going on there. Okay? So before jumping into these symbols and trying to analyze these symbols, what should we do? So all these symbols are about F and G and F inverse and G inverse. Danny has an idea.
State your variables. Get a better understanding.
Okay. So can you be more specific? What do you mean by that?
Like give F, write out F, what is F, what kind of function is it, and then write out what is X and what is it.
Okay, right. So if we want to really know very confidently what the function F is, what the function G is, what F inverse is, and what G inverse is. What would it take to really know those four functions well before we jump into these symbols? What will it take to really know those four functions well? Write the function notation. Well, that's what these symbols are. All these symbols are function notation. Yeah, so to understand these four functions, we need to know what the input quantity is and what the output quantity is of those four functions. So I'm gonna put you to work for a couple minutes. Hopefully you've looked at this, but let's look at it again. It's really important. So before you jump into the symbols, you got to write down, know confidently, what the input and output of all four functions is. F, G, F inverse, and G inverse. Once you have that organized and in front of you, then you have a fighting chance at making sense of all these symbols, the function notation. Okay? So let's take a minute to do that, and I will start attendance. Okay, so F, number of people expected. Is that input or output?
Output.
Output. All right. Input of F. Temperature. So therefore, F inverse, what's the input? Output is. Okay. G. Attendance. Output. Revenue. G inverse. Input. Number of people. Okay, so having that in front of us, now we can have a fighting chance making sense of these symbols. So A, does it make sense or not?
No.
Because G of 100 gives you revenue. Input into F is temperature, right? Output of G is revenue. Input of F is temperature. F says that's not my function. I don't do that. I don't take what? Revenue. I don't take revenue. I take temperature. Doesn't make sense. Okay? G of F of X equals 100. Output of F is number of people. Input of G is number of people. Okay, we got a match, right? So this will work. So what's that X represent? That's a temperature that will result in. Nope. So what is this overall? What is that expression? It's not number of people. Revenue. It's the output of G. That whole thing on the left, as a whole, is the output of G. So that's going to be revenue. So the 100 then is revenue. This is revenue. And so the meaning of the X then in this statement is. Who can say it? What is the meaning of this X? Mitchell, temperature. Any temperature? Which temperature is it? What's that? Okay, temperature degrees Fahrenheit. So, is it any? Could it be 80? Could it be 70? Could it be 60? In this expression? It's the temperature. You said the temperature that gives you the amount of people that would give you a revenue of 100 hundreds or $10,000. Yeah. So in this equation here, that X is specifically the temperature that will result in revenues of $10,000. Make sense? Cool. How about F inverse? So that's got to mean something, right? It's just by itself. So what is the overall meaning of that expression? Somebody new who wants to say, what is the overall meaning of that expression? Gives you temperature. So go ahead. Which temperature does it give you?
When there are 70 people.
Yeah. Yeah, so that's going to give you, that's the output of F inverse, which is temperature, when we expected, yeah, so it's the temperature corresponding to expected number of people of 70. Right. Okay, with this next one, G inverse X of 85. How about, I can't remember your name, tell me. Yep, blue shirt, yep.
G inverse of Gx is the number of people.
This is a number of people, so that 85 is?
The revenue.
It equals, so 85 equals this. What is this?
The revenue, sorry. The X is the revenue, and the output of that is the attendance.
Right. Okay, so this X is the revenue corresponding to, is it any revenue that we could get?
Revenue in hundreds of dollars.
Okay, so could be 100 hundreds, 200 hundreds, or is it a specific amount of revenue?
Total revenue?
The point is, it's a specific amount of revenue corresponding to this. Do you see? If we say that equals 85, now that amount of revenue is determined. So we can describe exactly what that amount of revenue is.
Revenue with 85 people then.
Right. That's right. So that X is the amount of revenue corresponding to 85 people coming to the concert. Right? So it's not just any amount of revenue that could change. Now we're locking it in and saying it's the amount of revenue for 85 people. Okay, so of E, F, and G, which one works? Do all of them work or just one? E doesn't work? Okay, output of G inverse. Number of people, input of F, temperature, doesn't work. Does F work?
Yeah.
Output of G inverse is number of people, input of F inverse is number of people. This one works. And then does this one work? Output of G is revenue, input of F inverse, number of people, doesn't work. Okay, so who can articulate what does that thing in part F? What does it mean, Matt?
It is the temperature when 80 people attend.
Temperature when 80 people attend. What do we think? I think I disagree.
Temperature in degrees Fahrenheit.
Tyler?
It's the temperature in degrees Fahrenheit when the total revenue is 80.
Yeah, what's the input into G inverse, Matt? You see that? So we're talking, yeah. So we got the fact that it's an output of F inverse. That's temperature. The whole thing means a temperature corresponding to an input into G inverse. So it's corresponding to revenues of $8,000 or $8,000. Okay, so we won't do any. If you want to talk about any others after class, I'm happy to talk about this. But is this starting to make sense? It's a really important skill to have. So, being able to use and appreciate function notation means really knowing, before you get into the symbols, what the input of the function is and what the output of the function is. And then interpreting that notation, knowing that the whole thing is output, right? Corresponding to the input right there. Okay, and so then the second page has good practice. We're not going to talk about it, but so if you're in today's recitation, you got a few minutes after class. If you haven't looked at this yet, if you're in Monday's recitation, this is good practice. All this stuff is good for working on input and output. Okay, so let's talk about this example here. This is a rocket example. So the graph, is that big enough? Let me make it a little bigger. Doing that. Okay. So here's this example. I'm giving you a graph. The graph shows f of t, which is the distance traveled by the rocket in meters, t seconds after launch. Okay. So before answering the questions below, we want to be real sure. Again, this is the same thing. We know the input and output quantities of f. All right. And then you got some tasks here. You want to represent the change in distance of the rocket. Represent, using function notation, the change in distance of the rocket from 0.5 to 2 seconds after launch with an expression using function notation. All right, so this is after launch. And then represent the average speed of the rocket from 0.5 to 2 seconds with expression using function notation. So this stuff is total fair game for the exam today. So good practice. Go. what you were writing.
Just not
Next time. This change in distance number 1A, total change in distance from 0.5 to 2. There you go. That's the change in distance. We want to get average speed. Average speed is calculated by right.
So how do you find an average speed? Right? So when they say average speed, it's not the same thing as averaging two speeds, right? Find so you are finding the constant. They would have had but how do you find the actual speed?
Yeah.
What? Figure of turns and changes.
Okay, let's see. Joshua. Chad. Is it Chad? How did A go? Tell me about A. Listen up. So this is what I heard you say. F of 2 minus F of 1.5. Oh, 0.5, yeah. How do you do?
Good.
Agree with that? Yeah, so you got the total distance after 2 seconds, total distance after half a second. So that change in distance will be the final value of distance minus the initial value of distance. Okay, average speed. How do we calculate average speed? Adam?
I just have a question.
You bet.
Would I be able to find that change if I did F of 1.5?
Okay, great question. So we're asking f of 1.5. Is it equal to f of 1.5? Yes or no? Some are saying yes, some are saying no. So tell me your name again.
Jacob,
Jacob. Why not?
because for two different inputs, like it's not going to be the same. 1.5 is not going to be the same input as the two different inputs.
Okay.
It's not
Jeff.
a constant rate of change. So if it was a constant rate of change, then it might be true.
Okay.
In this case, it's not. So it's not true.
And why is it not true?
Well, for the input of 2 in F, you get a specific value.
Okay.
Input of 0.5, you get a specific value.
Okay.
But if you subtract them, you don't get the same values as input of 1.5.
All right, more comments. Yeah, okay, that's right. Eric?
So since it's increasing exponentially, if you have two inputs, say f of 20 and f of 18.5, you still get the difference of f of 1.5, but f of 2 minus f of 0.5 isn't the same as the difference of f of 20 minus f of 18.5. Because it's increasing exponentially, the numbers are so much
Okay. Yes.
The one on the left gives you the change in two quantities.
Right.
While the one on the right gives you a point X specific.
Yeah, so exactly. What does this give you? What is it about? No, it doesn't give a point. What does it give? A distance. What? 1.5 seconds since launch, right? So this question is about meaning. It's about the meaning of those symbols. What does the left side mean? What does the left side mean? Change in distance, starting at 0.5 seconds and ending at 2 seconds. What does the right side mean? Distance traveled since launch. Do you see that those are the meanings are totally different. So what some people said was, maybe the values end up being the same, but usually not. And the real question is about meaning. Those meanings are totally different. The one on the right is the distance since launch at 1.5 seconds, which has totally different, and for the most of the time would be a different number than how much the distance changed starting at 0.5 seconds, ending at 2 seconds. Okay, great question, okay? So now we want to represent the average speed. So this is a big no, right? So this is no. It's easy to think that might be true, but think about the meanings of everything, and you'll see that it's not. Okay, average speed. Yeah, Chad.
Since average speed is defined as a certain amount of distance covered over a certain period of time, since we have 0.5 and 2 seconds, we can use the same function as above for the delta d. So we put f of 2 minus f of 0.5.
Good. Change in distance.
And then the change in time, we can just put 2 minus 0.5 or 1.5.
Right. Exactly. So you could put 2 minus 0.5, change in time, or you could just put 1.5 because that's out what the change in time is. Okay. So now, how would we be able to? So that is a number, right? That average speed is a number. Before we do C, let's talk about what is the meaning of that number? No. Let's get the number first. So how would we calculate that value? Then how would we calculate that value? Yeah, Benji.
So you find the distance traveled at 2, and then you find the distance traveled at 0.5.
Yep.
You subtract those and you divide it by 0.5.
That's it. So we would need either you're going to pick off outputs y values from the graph to get the output at 2 and the output at 0.5, or we can just I've got this. It's in there already because the curve is there, so I can just f of 2. So there's our distance at. It's bigger. Okay, so there's our distance, f of 2. So after 2 seconds, the rocket is 95 meters from the launch pad. If I do minus f of 0.5, we get that change in distance and starting at 0.5 seconds, so about 89 meters. And then I can divide that by 1.5. And we get 59.6. What's the units? What was our meaning of average speed? What was our meaning of average speed? So tell the person next to you, according to the meaning that we developed for average speed, what is this 59.6 meters per second? Go. Okay, so the meaning of average speed that we learned. So this is the average speed of our rocket. How do we make sense of that average speed? So tell me your name in the light blue. Yes, yeah.
Yes, so basically, that speed quantity represents like how it would travel at a constant speed and would travel the same distance of the speed.
He said this is like, so we just get one number when you do average speed, right? But this rocket is speeding up. So that one number has to be what? A constant speed. So which constant speed is it?
The constant speed between the time of 2 seconds and 0.5 seconds.
Of our rocket?
The time it takes to travel that distance. Like the average speed.
But our rocket is changing speed, and this is a constant speed. So what constant speed is that?
It's a constant speed required to travel the same distance as that constant.
Yeah, so that's what, and that's, what's your name again? Nick. So it's the constant speed, like of a different rocket. You got to think there's like a different rocket, and it's going at a constant speed. And what's it going to do? It's going to cover that same distance, f of 2 minus f of 0.5, in over the same time interval from 0.5 to 2. Okay, so it's the constant speed to go the same distance in the same time. You got to think of like a second rocket. You give a second rocket, they're both at 0.5, they're at the same height. That second rocket's just going to cruise, right? Every second it's going to go 59.6 meters. Our rocket's going to speed up through that time, but they're going to achieve the same change in distance in that same amount of time. Okay, how many points are on my graph? 2, right? How many points? Infinite. Infinite. See if you're confident, okay? I just highlighted 2. All I did was highlight 2. There's an infinite number of points there. So what is the meaning? Say this point right here. What's the meaning of that point? What's the meaning of that point? What does it represent? Does the point mean a distance traveled?
Yes.
It means 2. It has its corresponding values of 2 quantities, right? It is both. It means that at 2 seconds, so that point represents the 2 quantities taken together. And that's what every point on that graph represents. A certain time and a corresponding distance that it's traveled in that amount of time. Okay? So what would, if we were to graph our second rocket according to this average speed, what would that graph look like? Okay, tell me more about that straight line. There's lots of diagonal straight lines.
Point of time of 0.5 seconds, 5 to point of time of 2 seconds, 2.
Right. So you're talking about those 2 points. Okay, so that's like our second rocket. Going at a constant speed, covering the same amount of distance, which is that vertical or horizontal? Same amount of distance. That's in this graph, that's vertical, right? That's a vertical coordinate. So it's going to cover the same amount of distance in the same amount of time. So both those 2 rockets cover this much distance from here to here. That's f of 2 minus f of 1.5. Over that same time interval. The one just does it by, our rocket does it by accelerating. The average speed rocket does it by at a constant speed. Okay, cool. More questions? So now we're going to kind of use all this stuff to build new stuff, but this is all great practice for your test. Go. This is a little tricky. You got to think about this. You got to work on this. I want to see what you write. Write this down. I'm going to write these down. I want to see what you wrote. Good. We're good then?
That makes sense. Yeah.
You want to answer? Oh, yeah, you have a question. Okay. Margarita wants to answer. What's the starting time, Margarita?
The starting time is F.
No,
No,
starting
starting time is
1 second. And now, here's the key. What's the ending time?
Any time is H plus 1.
So if it lasts h seconds starting at 1, then the ending time from the beginning is h plus 1. So now, what's the change in distance starting at 1 second, ending at h plus 1? Want to keep going?
Yeah.
Tell me.
Okay. So the change in distance traveled is F of H plus 1 minus F of.
Right. It's going to be the final distance minus the initial distance. So lots of you got it. That was good. Lots of you got that. This is a harder thing, but it's important. All right, now we want the average speed for that change in distance, average speed. Aton.
Aton.
Yeah, got it.
F of h plus 1 minus f of 1
Mhm.
over h.
So we take that change in distance, and we need to divide by the change in time. What's the change in time?
H.
So yeah, you could do h plus 1 minus 1, but that's just h. And if we go back to the original problem, we know that's the length of the time, h seconds. So yeah, h plus 1 minus 1 for the denominator, perfectly fine. But do the math, you get h, and that makes sense. It's an h second period. Okay, keep going. Oh, so let me just show that on the graph. So what, h can be anything, and we want, so what are we talking about there? This is an average speed, right? This is an average speed. So it's like we're starting at, it's like always starting at 1 second, but then that time can vary. So here's h 2.1, here's h 1.6, here's h equal to 1. So we have variable time length of h, but the starting time is always 1 second. So depending on the value of h, we get different average speeds, depending on how long of a time period we... What is it about that line that represents the average speed? Oops, wrong one. What aspect of the line, or quality of the line, is representing that value of average speed? Isn't this the change in distance in our graph? Isn't that the delta what? Delta y, or delta d, but for our y and x coordinate? Isn't that delta y over delta x? Okay, so then what quality of the line is that value of average speed represented by? The constant rate of change, or the constant rate of change, or the slope of that line. Because the slope is the change in y over change in x. So the slope of that line, not the steepness, okay, not the steepness of it, but the change in y relative to the change in x, okay? So that's the slope, or the constant rate of change. Okay, keep going. Here's number 3. Now we're really generalizing it now. Starting at any time x seconds after launch and lasting h seconds. Okay, somebody new. So, Christopher, did you get it? Tell me. Or you didn't, or you did? You did not. Tell me your name again. Evelyn, did you get it? Tell me.
Change h plus x minus
F of? That's what you should have had. Oh no, sorry, just change. The first one's just the change. That goes here, right? So part 3a is just your numerator, and 3b is the whole ratio. Okay, so now so this is what's called the difference quotient. This result of b is the difference quotient. Why? Because it's the difference of outputs And the difference of inputs, this is actually x plus h minus x, which we know is h. So you have the difference of outputs, the difference of inputs, and we make a quotient out of that. What value does when you have distance as output and time as input, what does the difference quotient represent? What value will you get from that difference quotient? It's okay, so relative to our rocket, average speed, right? It's the equivalent constant speed, which is the average speed of the rocket. Starting at time, what? Starting at any time x and lasting for, how long is the duration of the time? H seconds. So starting at time x, lasting h seconds. You get the average, the difference quotient gives you the average speed over that interval. Okay, so here, this function now, I'm going to tell you what the function is. It's 23.84 times t squared. So you're going to write out the set of instructions that f executes on the input. Write out the set of instructions. We practiced this with our inverses, right? So go ahead and do that. Write out the set of instructions that f executes on input. Okay, so you should have gotten it. It says to square the input, and then take that result, multiply by 23.84. Yep, good. So using those instructions now, rewrite this difference quotient, f of x plus h, minus f of x all over h. Rewrite that according to your set of instructions for any time that f is employed. So you're going to actually do it twice, right? You're going to do that set of instructions on input here, and do it here, and then rewrite this whole expression by replacing these two with what it's telling us to do with f, right? Does it make sense? So what is the input here? F of x plus h. X plus h is the input, right? So what does the rule say to do? Square it, and then multiply by 23.84. I'll just do 23.8. And then minus, what's the input? X. Function says to square the input and multiply by 23.8. And take that whole thing, divide by h. So for our particular function, this is also the difference quotient. So we're actually executing the function. We're taking the input, following the set of instructions that it says, square the input, multiply by 23.8. So for this particular rocket function, that expression is the difference quotient, or the average speed of the rocket starting x seconds over an h second time period. Okay, I will stick around and answer any last minute questions you might have. Both of us will. But be there, you're going to be there by 10:15 if you got the exam.